Hi everyone and welcome to the last part of chapter 6. In this part we will learn to build a noise pollution monitoring system. Noise pollution is a critical issue that often goes unnoticed in our ever-expanding urban society, ultimately affecting our overall well-being and quality of life. Fortunately, we can address this problem with the help of PTM microphone and EDU PICO. By learning how to use these tools, we can effectively measure and analyze the noise levels in our environment. In this video, we will program a fully functional noise monitoring system that allows users to input an acceptable noise limit. With the help of the potentiometer, we can adjust the noise threshold. If the noise received from the PTM microphone exceeds the threshold value, the RGB LEDs will light up in red, indicating the space is too noisy. If the noise is below the threshold, the RGB LEDs will light up in green, indicating a safe noise level. Let's begin with writing the code for this activity. Line 1 imports various libraries and modules such as board for pin definitions, time for delays, new pixel for controlling RGB LEDs, bus I/O for I2C communication, array for creating arrays, math for mathematical operations, audio bus I/O for audio input, and Adafruit SSD for the OLED display. Line 2 imports analog IN from analog I/O module for reading analog input. Line 11 to 12 initializes audio input using the PTM method from the microphone connected to pins GP3 and GP2. It sets the sample rate to 16,000 samples per second and a bit depth of 16. It also initializes an array variable to store the audio samples. Line 14 to 15, sound minimum and sound maximum determine the minimum and maximum sound level thresholds that will be adjusted using the potentiometer. Line 17 to 18, this function calculates the base 10 logarithm of a given number x. In many scientific and engineering applications, sound levels are expressed in decibels, and the logarithm base 10 is commonly used to calculate these levels. Line 20 to 23, this function calculates the root mean square value of a set audio samples. The RMS value is used to quantify the magnitude of an audio signal. Line 25 to 28, the calculate sound level dB function calculates the sound level in dB by first finding the RMS magnitude of the audio signal and then converting it to a logarithmic scale with a scaling factor, making it a common method for expressing audio levels in a more human-readable form. Line 32 records audio samples from the microphone using the mic record method. It captures a number of samples and stores them in the samples array. Line 33 calls the calculate sound level dB function to calculate and return the sound level in decibels using the audio samples from the microphone. Line 34 reads the value of the potentiometer, maps it to a range between sound minimum and sound maximum, and stores the result in the pot value variable. This value represents the threshold for determining whether the sound level is high or low. Line 36 to 38 update the OLED display with the text information. They display the sound level dB label, the actual sound level in decibels, and the threshold value set by the potentiometer. Line 40 to 42. Here, the code checks whether the sound level dB is greater than the pot value. If it is, it fills the RGB LEDs with a red RGB value of 25500 to indicate a high sound level. It also displays sound level high on the OLED display. Line 43 to 45. If the sound level is not greater than the threshold, it fills the RGB LEDs with green RGB value of 25500 to indicate a low sound level. It also displays sound level low on the OLED display. Now, let's download the code and try it out. Having an OLED to display noise decibels is great. However, in practical usage, the OLED may be too small for everyone in the surroundings to notice. In this challenge, we will solve this problem by integrating a servo motor as a noise indicator, reflecting the values displayed on the OLED but in a physical form with a larger view. The code here should help get you started. Fill in the missing code with the appropriate information based on the description given. This is the final code for the challenge. Let's build the servo sound meter and give it a try. Well done completing chapter 6. In the next video, we will explore how to use the DC motor and relay. Thanks for watching, and I will see you in the next video.